coffee today to get me through the day. And now you notice that there's no puddings, so we have to maybe talk to Thomas about this. Okay, so today we are going to take everything that we've learned so far and apply it to an actual real-life situation, namely that of black holes. I told you before I'm going to do 3 real-life situations with you. Black holes is one of them. The other one is cosmology, the universe as a whole, and finally gravitational waves in no particular order. I decided to start with black holes because for many reasons this comes with the least extra assumptions. Because black holes, everybody knows these as these ridiculously difficult things in physics, and actually they're one of the simplest. And it don't mean mathematically simple, because of course it's mathematically complicated and such, but they really do come with only a very small amount of properties. Black holes only have mass, and they have spin, how strongly they're rotating around its own axis, and in theory they could also have an electric charge. So there's really only 3 types of black holes. Massive ones, massive with spin, and massive with spin and charge. We're going to look at just the massive ones. The spin ones are not more complicated mathematically, it's just it takes more time to work out the algebra. So we're going to use the simplest case, but that means it is a simple object. You only need the mass, and that defines the whole black hole and everything in it. Now, name me one other thing in physics where you only need one number and you can calculate everything about it. There are not that many, is what I'm saying. So in that sense of the word, a black hole really is the simplest case that we can look at. If we're going to do cosmology next week, and you will find that, well, cosmology comes with some extra numbers. You need more than one number. In that sense, it's more complicated. So that's the plan for today. Let's get started. Yes?
Wait, so this lecture won't be on the exam?
No. And we still have to set the date for the exam, though.
Oh,
We haven't done that yet. Remember? So let's reserve that for later. I was thinking about this, and I thought, well, we really don't have to restrict ourselves to one of our lecturing days, right? I mean, if for some reason people say, well, agenda-wise, it's good for everybody to do it on, say, not a Thursday. Well, Thursday was Ascension Day, but one of the other days, that's fine too. So let's think about that for a while. Get back to it later. All right. So for the exam, it's up till this point. So everything that I'm going to tell now is not on this midterm. But speaking of the exam, maybe it's good to have a little summary. So just as a series of steps, if you do relativity, because of course we're going to need this. To do relativity, general relativity, you might want to memorize this for exam purposes or so, or just any other situation where you do relativity. You start with the metric, yes? This is all just recapping what we've seen before. Take the metric. Metric tensor, G, alpha, beta, and you should now know what this thing means, yes? If the question is, I want to now know how things will move in this curved space-time, that's defined by this thing, what do I do? That's the question, because this is what we're going to do today. Apply to a real-life situation. So in general, what is the next step?
Do this contraction with it?
With what?
With the metric tensor?
Yes, but contraction is with something.
Oh.
Well, Christopher's symbol first.
Yes, you calculate the Christoffels. And yes, indeed, I mean, the calculating Christoffel comes with contractions. That is very true. Calculate the Christoffels. We practiced this last week, and we found that even though in principle there's a big number of these things, if you just look cleverly at what your metric looks like, you easily find that most of them are 0, and it's only this, and this one that is not 0. Calculate Christoffels. So we have the Christoffels. Quick follow-up question: what does a Christoffel symbol sort of give you, physically speaking?
Force.
It's like a force. It's not exactly the force, but it's like a force, right? Because it plays the exact role as this thing that is equal to the second derivative of a position. So that makes it a force-like thing, apart from maybe a dimension or the unit or something like that. But it plays the same role. So yes, that's the role. Follow-up question. Maybe from your classical mechanics, if you have a force, you can typically write it, well, it depends on your circumstances, but for conservative forces and such, you can write this as the gradient of something like this. It's usually defined with a minus. And this thing is then called the potential. Now, knowing that your force, well, if you've never seen this, don't worry about it. But you can, right? And for the electrodynamic people, this is of course also what we did. We wrote our electric fields and our magnetic fields in terms of potentials. And back then I told you, well, a potential really is this thing that if you take the derivative, you get something physical back. That's what we do here. You have this thing, potential, you take its derivative, you get back something physical. Just in our situation, if you know that the Christoffel symbol is like a force, has the same mathematical or the same physical interpretation as a force, and you know that it's a sum of derivatives, right? I mean, it's some combination of derivatives. What would this thing be, physically speaking?
Potential.
A potential. That's true. So here's a new interpretation of what a G mu nu is, a metric tensor. It's the gravitational potential. I introduced it as this thing that tells you what the numbers or coefficients are in your line element, with what number you should multiply dt squared and dr squared and theta squared, which is mathematically true. I also told you that's a measure of how strongly your space-time is curved, because if it turns out that it's just unit, that means you just have Pythagorean theorem and you have no curved space-time. But apart from that, apparently, physically speaking, it has the properties of a potential. Now, if you're not picking up on any of this, don't worry about it. It's just giving you some connection to the rest of physics. Okay, so we have the Christoffels. Remember what I want to do was I have a curved space-time. I want to know how things move in that curved space-time. Start with the metric, calculate Christoffels. What do we do next?
Substitute them into the geodesic equation.
Exactly. In the geodesic equation, because, as you know, equations is plural. There's 4 of them. Every space-time coordinate has one. As you know, the geodesic equations are these equations that tell you how things move in a curved space-time. And we found these things, the geodesic equations, by observing that things in the curved space-time should move such that the proper time is the minimal amount of time. Which is the same thing if you think about it. I mean, if I throw something in a gravitational field, I throw this cup of coffee around or so, then the thing knows where it's going to land, and then decides, well, how should I fly through this space in such a way that the amount of time for me to get there is the smallest. That's what this thing does. And of course, in the tutorial, we will see how this thing comes about from that idea. Well, that's fine. We're going to, if there's any parts that are missing, we're just going to fill up until we have a complete mathematical solution to this. But that was the idea of the geodesic equation. It's the equation that tells you how the proper time is minimized. And if you know that the proper time is minimized, that is the path that things will take through a curved space-time. Then this will tell you the equations that things will follow in a curved space-time. Now the next step, of course, you have to solve them still. These are just the equations. You still have to solve what the actual motion is. And here, unfortunately, is the difficult part. Because solving the geodesic equations is typically mathematically very cumbersome. Solve the geodesic equations. We talked about this on Thursday. Unfortunately, geodesic equations are 4 equations. They're coupled. One of them requires the solution of the other one, but the other one requires the solution of the first. So they grab each other hold and they don't let go until you've solved all of them in one go. That's one thing. The second thing is they're nonlinear, which means that all your usual backup tricks for differential equations do not work. In fact, it's even uncertain how many solutions are there in the first place. This is very different from linear differential equations, where if you know what the order is of the differential equation, you know immediately how many solutions there are. No such luck here. Not only do you not know how many solutions there are, you have no idea how to get any of them. So there's tricks to do this. Sometimes they work, sometimes they don't. This is not the same as saying that there's no solutions, it's just there's no standard trick. You have to start from scratch every time that you try to do this, unfortunately. Okay, and there we are. This is how you do general relativity. At least the part where, given a curved space-time, you calculate how things move. There's still the question where this comes from. And I hope to give you some glimpse of that today. Take a sip of my coffee here. Very theatrically. No, nobody's going to ask about this.
Was that?
Okay, thank you.
Was that from the Einstein field equation?
No, the Einstein field equation is the one that should be here, that gives you the metric.
Yeah.
No.
Yeah, you were.
Yeah, oh yeah,
saying.
that's one. So let's do this again. Okay.
See the photo.
Nobody know? Really? Just amuse me for a second. Yes. No, sorry, no. So I thought you had something to say, or maybe to ask. Yes.
So what's the missing one?
Oh yeah, it's good that you ask, because what's missing here is something that we haven't encountered so far yet. There is an extra step that for all the spacetimes that we looked at, which was really just Minkowski spacetimes, that wasn't very necessary. So I'm going to put the words here, and we're going to see how this works out in practice when we do the black hole thing. Namely, identify who measures what. If you don't know what I mean by this, again, don't worry, we'll do this in a second, but just very quickly put, your metric tensor gives you this thing called a line element, yes? This many times the t squared, plus that many times the r squared, plus that many times the theta, plus that many times the phi. Now, up to this point, we always said, well, dt is the time measured by this person, and dr is the amount of distance measured by that person. That trick does not always hold. The dr is not necessarily the amount of space, distance, measured by an observer. And if it is, which of all the 15 observers is it? Remember that even in special relativity, one person's distance is not the other person's distance. One person's time is not the other person's time. So what you have to do is identify in your metric tensor all the r's that you might have, and the t's and the phi's and the thetas. Who is the observer measuring those exact numbers? So that's a step that we haven't really encountered yet, but we will encounter it today. So this is a general thing. This is not just for black holes. Generally, if you want to do general relativity, how things move in a curved space-time, then you have to do through these steps. That series of steps always works, and this is a very important one. All right, this is it. Any questions before I start with the new stuff? This is not a trick question as I did before with the cup of coffee. This is a real question. If not, let's get started. We'll start right here. I'm going to give you a metric tensor. It's called the Schwarzschild metric tensor. And of course, you know it from the project. Do you know it by heart still?
I thought I did, but I just don't remember that I had it slightly wrong in my head. I think I do know it now, though.
Okay. Now, I'm not telling you where this comes from, because that's a step we've been skipping up to this point. We just take a metric as given and calculate everything from that. I will say something about where this particular one comes from, but yes, let's see if you...
It's diagonal one again?
It's again diagonal, so there's only non-zeros on the diagonal. That's true.
The first element was 1 minus 2m over r. I don't know with the, I only knew it from the C is 1, G is 1.
Yeah, because when we did this before, we worked with G is 1 and C is 1, and I promised at some point that I will not do that in this course. So I'm going to put the G's and the C's back in.
Your G is gravitational constant?
It's Newton's gravitational constant. So it's not small g, 9.81 meter per second squared, it's the big universal constant.
And the second one is the same thing, but then inverse and negative.
Okay. This is correct.
There's also it's a negative in front, right? Negative sign.
I'll get back to the negatives in a second, yes.
It becomes r squared, and r squared is sine theta squared.
R is sine squared theta.
Oh,
It's not the sine of theta squared, but
Yeah.
I'm sure that you meant that. Yes, and all the rest are zeros. 0, 0, 0, 0, 0, 0, 0. So that's good news, because that means that most of the crystals are going to be 0. Now there's a minus sign issue. Remember from the first lecture I said that in these metrics, or in your line element, where you do the Pythagorean theorem in space-time, there's always one thing with a minus sign. And the fact that that is true is called the Lorentzian signature. You cannot have any relativity without this overall minus sign in one of the terms. And it's always a matter of convention where you put it. You might put it in front of the time or the space part. And which one you do really depends on what lecturer you happen to have, what author or what book. And they're all fine as long as you stick to your convention. Back in the project, we used the minus sign here.
Yeah.
But when I started this lecture series, I started with the thing here.
Okay.
So they both work, again, as long as you just stick to your choice. This is indeed a Schwarzschild metric. Fun fact, when Einstein had his Einstein field equations, from which these metrics follow, he thought this thing is so ridiculously difficult, mathematically speaking, that nobody's ever going to find this. Find any solution, only approximate solution by approximation schemes. This is much more difficult than solving the geodesic equation, because this is only 4 equations, and they might be coupled and nonlinear, but sure, okay, that's fine. A metric has 16 numbers that you have to find. Now, a metric happens to be symmetric, in the sense that whatever is here is the same as here. And if you count then the amount of unknowns, it's 10. But the Einstein field equations, the one that gives you what these numbers are, what gives you what the whole metric is, are then 10 coupled nonlinear differential equations for these 10 numbers. And Einstein thought no one is ever going to find full analytical solutions to this. Only approximate solutions. He himself, when he presented his general relativity in a series of 4 papers, I think that it was at the end of 1915, he solved them by approximate methods. He said, well, it's sort of like this-ish, and the amount of error is only this many percent or so. And he found all these interesting effects like the deflection of light and such. So he thought nobody's ever going to find a full solution. Much more difficult than this one, and this one was very difficult. And then 3 months later, Schwarzschild found the first actual solution. This is an actual full solution. And Einstein was very surprised. He said, oh, okay, that's unexpected. But Schwarzschild found this thing. Even more interesting is that Schwarzschild found this in the trenches of the First World War, because he was a soldier and was sent to the World War, and bombs were flying over him. He was doing this calculation and found this thing. And it is indeed the first full solution to the Einstein field equations, the thing that gives you the metric. So there's a fun fact. It's also quite ubiquitous because this thing applies in any situation where you have a spherical distribution of mass or energy. You cannot tell immediately just by the looks of this thing, but later on people found that if you have a certain amount of mass in space, and this mass distribution is spherical, so that means there's as much mass in this direction as in any other direction, spherically symmetric, then there is only one solution, and that's this one. This fact is called Birkhoff's theorem. And that's very important because that says whenever you have a spherical mass distribution, you don't have to look for new solutions to the Einstein field equation. It's always a Schwarzschild metric. So, now name me a couple of things in the universe that are spherical, have a spherical mass distribution. I mean, there's planets, there's stars, there's neutron stars, there's black holes. For all of this, you can use this one, under the assumption that it does not rotate, because otherwise it gets more complicated. Was that your question?
Some black holes rotate, right?
Yes, most of them do, in fact.
Okay.
So that
But
means
not all of them.
no, I would say that all of them do. but in a varying amount. So that means that this thing itself is only just an approximation to rotating ones. Now later on they found another solution that includes the rotating part, a full solution to the rotating one. And as I said at the beginning, that metric, it's called the Kerr metric, happens to just be more complicated because you now have to take into account angular momentum. It doesn't change any of these steps, just the algebra along the way. So I'm going to use this one. Yes?
But can we assume that, for example, that neutron stars are like perfectly like round, like sphere? Because like the Earth, for example, is not perfectly.
No, it's a little bit oblique, but the amount is very small.
Yeah.
So this really only applies to extremely spherically things, but the deviation from this, if we just calculate how bad it is not bad.
Okay.
So it's only when you want to apply this to, I have no idea, I mean this extremely flattened pancake of a planet or something like that, then it doesn't work anymore.
And you can apply this to black holes.
Yes.
So you assume that black hole is like kind of a sphere.
Yes,
Okay.
yes. And back to Einstein, when people calculated what the consequences are of this thing, and one of the things is going through these steps, is some strange properties come out. And Einstein thought, well, I just don't believe, physically don't believe that these things exist. It happens to be a mathematical solution, but then again, who says that all mathematical solutions I should take seriously? Even if the physics is correct, why should every solution be one that physics or nature has actually used to manifest in real life? So Einstein never, at some point he turned around I think, but he thought at first that this thing is only a mathematical curiosity. The thing does not really exist, but now we do. We now know that they do. So there's that. Now we can go through these series of steps, and we will, but let's first see if we can see some properties of this thing, just the metric itself. Now, question to you. There's an m in there, and I'm sure everybody thinks, well, there's an m that's probably a mass. Can you see that it's not a priori clear that this should be a mass? It just says a number called m. Who says that that's a mass? It is. It's the reason why I put an m there. But how would you be able to tell? Just from the, yes, well, go ahead.
I would say, like, I would assume it's a mass because it's next to the G, and we use G.
Oh, yeah, because Newton's gravitational,
Yeah,
something like this, right? Well, you know what?
and the R as well
Yeah.
under it.
Okay, how about this? Does this look familiar to you? From your Newtonian mechanics, maybe? What is it?
Gravitational potential.
It's a gravitational potential. Look. There it is. And didn't I tell you just before that you can see the metric as a gravitational potential? So there you go. So this indeed is how you can identify that there should be a mass in there. Now, one step back. By the way, how do you make a gravitational force out of this? If you have a potential, this is the potential.
It's R squared.
Sorry.
It's R squared.
But you're not just free to just put. I mean that.
No, for the force.
Yes, that is true. But how do you get it in?
Ah.
The derivative.
Yes, a derivative. But to be more clear, you have to take the negative gradient of that thing, and it will give you Newton's universal law of gravitation. Now, if you cannot make this connection to Newtonian physics, don't worry about it. But all I'm just saying is this connects to the idea that I introduced just a second ago, that the metric corresponds to potentials. You take derivatives and it gives you forces. So immediately you can tell, wait a minute, there's a 1 over r, so that by itself sort of suggests that this should be a gravitational potential, and as a result there should be an m in there. Now, to make this connection more explicit, I've made an exercise where I guide you through how you get these exact numbers in. Okay, so there's an exercise on how you do this in full, but it's closely related to this, of course. So that's very nice. Second question. What happens if the mass is 0? If you're in a space where there happens to be no mass?
You get in close on the close to butterfly.
It's
flat.
not broken, right?
Yes, because if you put m is 0,
Yeah, it's gonna be
0,
yeah.
0, and this should look familiar to me now. This is the Minkowski spacetime, written in spherical coordinates, but this is the uncurved Minkowski spacetime that we did on Thursday. So there we go. Apparently what we have here is we found a solution. Mathematics has forced this solution on us. And what we find just by inspection is, wait a minute, this thing looks such that if there would be no mass, it would be a non-curved space-time. So there's something interesting going on there. By the way, this by itself is an argument why there should be a mass in there. Because what is it that makes space-time curved? What makes gravity? That's mass. So you know that there should have been a mass in there somewhere. And if you take the mass away, you get an uncurved space. So you could tell that there should be a mass in there somewhere, right? So there you go. I mean, this is how you slowly can understand where this comes from, even if you haven't fully solved the Einstein field equations yet. One more observation. What happens if R is a very big number? You okay, Francesco?
No, I can't really see.
Oh, okay. What happens if you make R a very big number?
That term also like the 2mg over r squared also like approaches 0, which make r really big.
Yes. If you make R very big, then, and m is not 0, so we have a mass. It's just that R is very big. Note that I'm very clearly not saying that means that you're far away because of this step. I haven't specified yet that R is really the actual distance. This is that step that is now new. But suppose that it is, or it's related to the distance. So then making R very big says, well, dividing something by something very big makes it 0-ish. There you go, put your hand on this. Same here. You get again the Minkowski metric. So we have here something. I'm happy that it brings such joy to you, these mathematical observations. But what we have here is this thing, just by comparison to Newtonian mechanics, or just knowing that it's mass that curves space-time, we know that there's a mass term in here. The 1 over r comes directly from the Einstein field equations. And we see that if you take the mass out, or you keep the mass in and look at it from very far away, it will look uncurved to you. It will look like a Minkowski space-time. Now here you see the first identifications of maybe that there is a mass in the middle somewhere, and the further away from it, the less you see of it, the less curvature you see. Yes?
So do you actually, so if you look at like a black hole from really far away, do you actually see the space-time as being less curved because you are far away?
Locally.
Or is it that it just affects you less because you're that far?
It's both the same statement. If you are very far from a black hole, which we are, by the way,
Yeah.
okay, and if we do some physics here, then in our local surroundings, it looks extremely like a Minkowski space-time. Agreed? Now, a different question is, what if you are far away from a black hole, but you look at something going on close to it? Now, at that point, you cannot say, well, it's sort of Minkowskian. No, where you are is Minkowskian. What happens over there is different.
Yeah.
And that is one of the steps that we will calculate today. So, how do you do that step? Yes?
So the R that you would then use if you look at that stuff that's close to the black hole is then the distance from that stuff you see to the black hole? Not anymore your own R?
The answer is yes, but I haven't proven it to you yet. But the answer is yes.
So that's kind of related to the question of who measures what.
Yes.
Right? Okay.
The answer to this question, and I haven't proven this, but I will in a second, is that R here is the amount of radial distance, so in a straight line towards that mass in the middle, measured by somebody who happens to be extremely far away from the black hole. It's called a black hole from now on, or a mass. Could also be a star or even the sun or the Earth, but say let's call it a black hole. That this R is the amount of distance measured by a person who himself is infinitely far away from the black hole and is not moving. Only that observer will correctly identify this as the amount of meters radially to the black hole.
When you said not moving relative to
The black hole. He's not rotating around it, say, or moving closer or further away from it. This is this step I'm talking about here, although I haven't proven it yet, but that's the short answer to the question. So there we go. So you could, even just by looking at the thing and mathematically looking at it from different sides, you can already see there's something going on there. One final thing, Doesn't matter from what angle you're looking at this mass in the middle.
No.
No, because it's spherically symmetric.
Yes, exactly. So apparently whatever the thing is, it looks the same from all directions. So now if you go to a Kerr black hole, which is also rotating, that will not be true anymore. Doesn't change it changes the physics, of course, but doesn't change the series of steps. It just makes it more cumbersome to work with, because all of a sudden we have to take into account from what direction we're looking. So yeah, it is spherically symmetric. Now don't be confused by the fact that how can it be spherically symmetric if there is still a theta in there. That's because whenever you span up spherical coordinates, you always have to have it with reference to a z-axis. So you cannot do away with your theta. That's just a consequence of going from Cartesian to spherical coordinates. It's not a property of there being some preference in the system for a particular theta, say. All right, so there's that. So there's no enormous amount of things that we can learn from just looking at the metric. Now we have the metric. Next step is, well, let's write down the line element. Okay. The line element, as you know, is this thing. There's very little mathematics here. This is just a definition of the damn thing, what a line element is. And you remember that the only reason that we introduced this notation with the Einstein convention is to make very long expressions look short. Now in this particular case it happens that it's really not that long if you just write it out. So let's just do it for completeness sake. Just as some practice, can somebody tell me what I should, can somebody dictate?
So it's only going to be squares, right?
Yeah, all those values
Mhm.
just square common into
Alpha is
minus
beta.
Yes. That's that thing again. That there's a double contraction. You have to contract over the alphas and the betas, but it just so happens that this thing only works if alpha and beta are the same thing. So that means that we're only going to get a very small amount of total terms. The question is what the terms are. Let's write down what dx mu is here. Alpha. It's always c dt, and because we're now in spherical polar coordinates, we don't have dx but dr, we don't have dy but we have d theta, we don't have dz, we have d phi. So we have this thing, then we have this thing. So the question is, if you do the double contraction, what comes out? What is the line element?
That is 1, so the bracket 1 minus 2 mg over r c squared times, was it c squared dt squared?
Mhm.
Yes. Sorry, yeah.
There you go.
Minus, well, the same thing, so, and then times power minus 1,
And
r squared,
dr squared.
yeah.
Okay, yeah.
And then minus again, minus r squared d theta squared, minus r squared sine squared theta d phi squared.
There we go. Okay, here it is. Same expression, just written out in full now. Again, it just happens that this thing is simple enough that the fully written out version doesn't take 5 lines. So here is our Minkowski line element, our Schwarzschild line element. And just as in special relativity you can derive everything from the line element, the Minkowski line element, you can in Schwarzschild space-time, you can derive everything from this line element. Once you have this, you have everything. You're completely set. It's just a matter of prying it out mathematically. Okay. Next step. The Christoffels is one of the exercises, and you know how to do this, right? I mean, there's no physical difficulty there, it's just going through the algebraic steps. So let's go immediately to identifying who measures what. There's a dr there, so it's a distance, But who is the person who measures this distance? If this number, dr, is 4, that means between two events there's 4 meters. Between two exploding firecrackers, say, two events, there's 4 meters. But who's the person measuring the 4 meters? Is that the guy standing next to the firecrackers? Is that some guy standing far away? Is that a guy within the black hole? Is that a guy moving with respect to things? Numbers change from observer to observer in relativity. So this is the identifying step. You have to identify who is the person who measures this dr and who is the person who measures the dt. If you don't know who measures what, you can still go through mathematics, but you have no idea what your answers mean. You get, oh, look, I find that my function of r as a function of time is 15 times t. Okay, what does 15 mean if you have no idea what r is? That's the whole thing here. So you really have to make this identification step. I'm going to make the identification for dt. Who is the person who measures this amount of time? That's two exploding firecrackers somewhere in this Schwarzschild space-time. Let's say there's 2 seconds in between. Who is the person who measures the 2 seconds between the two events? That is my question here. The dr part, of which I already gave the answer, is the distance measured between two events by somebody who's infinitely far away and is not moving. This again is an exercise for the tutorial, but it follows the same steps that I'm going to do right now. So, question to you, do you remember what this thing means? The proper time. Physically, what does it mean? What is that thing?
When two events happen at the same time.
Same time?
Location.
Same location.
Yes.
That is very true. You remember this from special relativity, d tau is the amount of time that passes between two events for somebody who sees the two events happening at the same place. Okay? Alright, so there's this guy, and he sees two firecrackers explode at the same place. So what I'm going to do now is I'm going to identify dt at the same place. What does that mean about what does it say about dr, d theta, and d phi?
All 0.
They're all 0. This is very important. We already knew from special relativity, this is the amount of time between two events as seen by somebody who sees the two things at the same position. Doesn't have to be his position, it's just a position. Firecracker explodes over there, and 2 seconds later another firecracker explodes at the exact same place. That amount of time, measured by that guy who sees it at the same place, that is d tau. But if the two firecrackers explode at the same position, then that means that there's no radial difference between the two events. There's no angular either. So that means this is 0, that is 0. So for a guy who sees them explode, the two firecrackers, at the same position, the whole line element reduces to this thing. And the rest is 0, yes.
But if our distance is 0, don't we have like a 0 on the...
No, dr is 0.
Okay.
R and dr are separate things. Dr is the difference between the two positions where the two events happen. That one is 0 because they happen at the same place. That does not mean that they happen at position 0.
Okay.
But you're right, it means something happens if you put R0, which is in the center of the black hole. So there's a question there. So this is not 0, it's just a number. A fixed number though, it's a number. Huh. What happens if I make R infinitely big? What happens to this expression?
Just reduce to c squared d tau squared is c squared dt squared.
Okay. We've seen this before. If you make R very big, and this drops out, goes to 0, and you just get back c squared d tau squared equals c squared dt squared. Or if you will, d tau is dt. Do you now see the conclusion? What is the conclusion? Not just mathematically, what does it mean physically?
If you're really far away, it doesn't affect your time or the time of the observer. Wait. Yeah.
Which both two observers? I never introduced two observers.
I think the observer like infinitely far away, or with R is really big,
Yes.
would see their own time progress at the same rate as the time for like whatever event is happening in the black hole.
Or close to the black hole.
Yeah.
Exactly. The tau is the. I'm sure that this is a variation of what you meant. Let's put it in those terms. Suppose you have two observers. One observer measures this, d tau, the other one measures dt.
Yeah.
Apparently, these two observers are the same observer if you're far away. What I'm saying here is dt is the amount of time between two events as measured by somebody who is infinitely far away. That is what it says here. It's important that you understand the reasoning here. Yes?
Isn't it kind of weird that you made the R equals 0, but you're still working with R later on?
No? Why?
Just they're the same R, right?
But if you're changing R0, doesn't mean that your actual R is also 0, right?
What is our radial distance between us?
R,
Okay, what's some number?
4 meters.
4 meters or so. Okay, so on the origin, you're 4 meters away, so that's R. Okay, now you explode, and a second later you're a firecracker, and a second later you explode again. First explosion, it's a hypothetical situation, but the first explosion happened 4 meters away, R is 4. The second explosion also happened 4 meters away, as seen from me, that's another 4.
Mm-hmm.
The amount of distance between the two explosions to me is 4 minus 4 is 0. dr is 0. R itself is not 0.
Okay.
So what I did here was I put dr 0, and by the same reasoning d theta and d phi. That's not the same thing as saying that r itself is 0, that theta itself is 0, or that phi itself is 0. There's a difference between an r and a dr. One is the actual value, the other one is the difference between two values. So let's go to the steps again. This is the general line element. My question was, what is this number? What does it mean physically? Then I say, wait, if I look at two things that happen at the same position, and I do it from infinitely far away, then the whole line element reduces to this here. Now I already knew what d tau was. It's the amount of time between two events as seen by an observer who sees them at the same position. And I found now, and if I go infinitely far away, that is that amount of time. Conclusion. dt here is the amount of time between two events, but only for that one observer who is infinitely far away. It's very important. Interpretation of dt. Amount of time between two events as seen by someone this is not a very nice looking infinity sign. I can do better. There. Infinitely far away. Oh, and also that person should not be moving. Now where did I put that in? I did it implicitly. The person doesn't just have to be infinitely far away, he should also not be moving. Why is that? Sorry?
So we go for
You said time instead of specifying space between two events.
Yes.
You didn't put space in the definition.
That is very true. Let's take you again, you're going to explode twice. But in the meantime, I'm not stationary, I'm moving with respect to you. One explosion happened 4 meters, that's now. And a second later, there's your second explosion. And that's not at 4 meters anymore, dr is not 0. The fact that I put dr is 0 specified that I'm not moving myself with respect to the two things. So it's amount of time between two events seen by observers infinitely far away and is stationary. So there you go. So now you know what dt means. So if we're going to calculate stuff in terms of dt and you find some numbers, you know, that's the amount of time measured by that guy far away. This is this step. You have to identify what things mean. The second one, That's the interpretation of dr, and that is an exercise, but it's interpretation that's extremely similar to what I've just now demonstrated for dt. That's what dr means. And I already gave it away when the question came. That's the amount of space in between two events for somebody who is stationary and infinitely far away. Radial space, radial distance. And that this is true, you can now prove for yourself. It's the amount of radial distance between two events as seen by someone who is infinitely far away and is stationary. So, yes.
So your r, not the r, just r. That's your distance.
Where you see the two events happening.
Wait, say that again.
Where you see the two events happening.
Okay. So your I'm confusing myself now. So if r goes to infinity, then your distance between where you see the two events happening is no. Wait.
No, that doesn't matter. I mean,
But yeah, you might be infinitely far away from those two events, but the radial distance between those two events is not infinitely big.
Exactly.
Yeah.
I mean, there's a distance between you, like a meter or something like that. It's still a meter, whether I'm standing here and looking at you or from infinitely far away.
Yeah.
It's just the R we're talking about, not absolute R's.
Yeah, but my question is, what is absolute R then exactly?
Okay. Well, in a moment, second half, I'm going to show you, I'm going to apply this for a real life situation. And you will probably get your answer there. Just
Okay.
when I
Yeah,
apply
because
it.
you just said something that it's the distance to the center of the black hole or something?
As seen by that guy, yes.
Okay.
Yes.
Is it a wrong approach to say that we're making r constant and therefore the r is going to be 0?
No, because this metric of this line element should apply to any two events. I've just happened to be taking two events that happen at the same position. I'm free to do that. What you could also do is say, well, you know what, I'm going to look at two events that are not happening at the same place. Suppose that there is a black hole somewhere in the middle and there is a star falling radially in. Then the r is certainly not going to be 0, because one moment that star falling in is here, and the second later it's going to be over there. Then the r is certainly not 0. So depending on your situation, you have to modify what the r and the t and the theta and the phi you're going to use. Now, what I did here was, the reason I took the r, the theta and the phi 0 for this interpretation is because I know what this thing means, d tau, but only if things are not moving. So I chose it for that reason. But generally you can use it for anything. Arthur, do you have a question? Okay. You see that this is a difficult step, this part, yes?
Could you explain the difference between d tau and dt?
Yes, d tau is the amount of time that passes between two events as seen by a person sees them happening at the same place. D tau, or dt, is the same amount of time between these two events, but as seen from somebody who is infinitely far away.
But this doesn't make sense, because two observers, like one observer can be next to the black hole, but there is at the same time. But this is not the case, right? Because of the gravitational deflection.
I'm not sure I understand. Why would
Why is the time next to the black hole like same as the time, like passing infinite far away from the black hole?
It isn't.
It is not.
No.
But that's d tau is equal to dt.
Oh, I see. Okay. Is it okay if I first do the example later and you see what happens there, so you can tell the difference?
Yeah, but this does not imply that time passes the same time. Like the time doesn't flow at the same rate.
No.
Next to the black hole.
No. I wanted to wait until the example, but here's a short attempt at answering your question, and then we'll do the explicit example. Then hopefully you'll see it happen in practice. Suppose I have these two events, and again it's going to be exploding firecrackers and going to be next to the black hole or so. Okay, and I am going to be infinitely far away, and I'm going to look at that amount of time between the two exploding firecrackers. I will get a number out. That number is going to be dt. Okay? Now there could be some other guy who's going to be standing next to the exploding firecrackers. He will measure another amount of time. So there's a difference between the two times. And what is your question? Because that is a short version.
No, I understood that d town is a time close to the black hole, or doesn't necessarily
No,
mean
no,
that.
no, no. It's the time measured by a person, wherever.
Where, yeah.
Yes. So it could be infinitely far away, could not be infinitely far away. Depends on the situation. I know exactly where the heart of your confusion lies, but it's much more easy to explain it while I go through the example. So this is why I'm urging. Is it okay to go through the
Yes.
example later and then you
Yes.
see it happen?
Yeah.
I mean, I know exactly where it is. Last short attempt, there's not one d tau in our situation. The two firecrackers exploding next to the black hole, and that being seen by somebody next to the firecrackers and somebody who's far away, both measure different d tau. And your confusion lies in the idea that there should be only one d tau, that the d tau of the one
Yeah.
person should also be the d tau of the other person. That is not the case. And the rest I will leave to the example. That's the short version. This is difficult, yeah? Understanding what the symbols mean. This also at the heart why people find general relativity difficult, apart from the mathematics. Constantly checking yourself if you understand what all the symbols mean at any moment in time. In time meaning going through your calculation. Here's the bad news. It so happens that in the Schwarzschild metric, this actually corresponds to somebody's measured time, namely that person far away who is not moving. And this actually happens this the R to be a radial distance as seen as measured by somebody, namely that person infinitely far away who is not moving. There's also metrics where these things that appear here are nobody's amount of time and nobody's amount of space. That there's nobody in that space-time who actually measures these numbers. So what does the thing then do? What's the point of having these things? Well, it's just a bookkeeping device. It just tells you that there is some number, even though the number is not measured by anyone in that space-time, that tells you how far away things have exploded and how much time there is in between. It's only by a lucky coincidence, in our case, that it actually corresponds to somebody's measured time. In fact, there is a way of rewriting the same Schwarzschild metric in different coordinate systems. And if you want to look this up, it's called tortoise coordinates, in which, I'm not making this up, it's an actual thing, in which the things that you have there, there's going to be dt and a dr star, and r star is nobody's distance. Now, don't get too worried about that. I mean, you have seen, I guess, throughout your physics courses, you have seen things that you yourself do not really measure. It's only if you have that thing, you can use it to calculate something else. An example again is the gravitational potential. You never measure gravitational potential. It's a number that allows you to calculate something else, say a force. In fact, you don't even measure a force. The only thing that you measure is how much something accelerates. So don't get too worried if you find that these numbers do not correspond to somebody's physically measurable thing. That is very often that it happens in physics. Yes?
You said before that there are like different d taus, but the result said at the beginning that d tau is invariant.
Aha. Now, when I write my lectures, as I'm not going to tell what order, just give me a second. I always try to anticipate what people are going to ask. Okay.
But this per time d tau or d?
Let's see, going to read it out loud. Some possible confusion. Why introduce different proper times, d tau, and this is the two proper times that I'm talking about. Wasn't the whole idea of proper time that everyone measures the same value? There's your question, right? Okay, so I was hoping that somebody would ask that. Yes. We have to be does everybody understand the question? The idea of a proper time, this thing in special relativity was, our whole starting point of relativity was that this number should be the same for all observers. Remember that? Was the invariance of the proper time, or the invariance of the Minkowski metric, as it was called then. And now I say just a second ago, with regard to your question, there's going to be multiple proper times, depending on where a person is standing in the space-time. So why doesn't that conflict with the idea that everybody should measure the same proper time? It doesn't.
Doesn't it depend on the metric?
That is a very good suggestion, that it just happens to be so that in a different metric, the taus are going to be different for different people. And it's certainly part of the answer, but there is a more elaborate version. It's an extremely good question, because it's the starting point of a lot of confusion if you don't get this out of the way. First of all, it has something to do with the metric. You can just tell by the fact that there's an R here that people are going to be measuring different things, right? The tau, the answer, what the number is going to be, depends on what the R is of that particular person. So you can immediately see there is going to be different d taus. So yes, has something to do with the metric. But how does this not conflict with my original statement that d tau should be the same value for all? Because that we haven't answered. We have now understood where the different d taus come from, but not why it does not conflict with my principle of d tau should be the same for all.
Is the C d tau only invariant in areas described by Minkowski space-time?
That is
Minkowski metric?
no. That's a rephrasing of your original statement. That if you go away from Minkowski, you get you're sort of breaking this rule. It's extremely subtle, but it's also extremely important. So here goes. We all understand the question, yes? Here's the answer. My statement was, if you go to some other observer frame, then d tau should be the same. So if you look at two things from one frame and then you start moving and look at the same two things, then d tau should not change. That's not what I'm doing here with my introducing multiple d taus. I'm looking at the same amount, but still in the same space-time. The only thing I've done, I've taken somebody who used to be next to the thing, he's now infinitely far away. I have not introduced any velocity, say. I have not moved into a moving system. He's still in the same Schwarzschild space-time, just at a different location. My original statement that the proper time should be invariant to changing coordinate system to another coordinate system. But my different d taus are not different coordinate systems. It's still this coordinate system. Still the same metric.
It's just different locations.
It's just a different location within the coordinate system. But it's still the same coordinate system. So I'm not breaking my rule. And here you see something extremely important. That was a follow-up note that I made. That we have something here that we had not had before when we did Minkowski. Apparently, our time effects are now going to be position dependent. That was not the case before. Before, difference in times and lengths only had to do with going from one system to another observing system, for instance via velocity or so, but there was no reference to where you were. Now we have a new way of making sure that you get different amounts of time and different amounts of space by where you are within the same system, even if you're not moving with respect to each other. Now this insight gives rise to a new version of both time dilation and Lorentz contraction. Back to Minkowski. The way that we got time dilation and Lorentz contraction was if you had two observers and they had a velocity with respect to each other, and as a result they found different values for their lengths and for their durations. That was because they were moving with respect to each other. What we now have is that even if they're not moving, they might still differ in opinion on how much time there is between two events and how much space there is, but not because of the relative motion, there isn't any, but because they happen to be at different positions. It's a new time dilation and a new Lorentz contraction, one that does not depend on velocity, relative velocity, but one that depends on position within Schwarzschild spacetime. Now this new version of time dilation and Lorentz, it's not called Lorentz contraction in this case, but let's call it Lorentz contraction for comparison purposes. This new version is called gravitational time dilation and gravitational length contraction. It's not due to your relative motion, it's due to where you are in the curved space-time, where you are in this gravitational field. So we have two time dilations in general and two length differences. One of them is due to relative motion, and one of them is due to where you are in the gravitational field. And I hope you see now, when you reflect back on Minkowski space-time, why we never encountered this in Minkowski space-time, because Minkowski space-time looks the same everywhere.
This doesn't.
And this does not. I'm going to make this explicit in a moment. I'm going to give you formulas for this new time dilation. How are we on time? Speaking of time, I think it's break time, so you can digest it. By the way, do you see? We haven't done any real mathematics yet. Do you see how much you can get from just knowing this metric? We can identify what the dt's and the r's means. We can tell that it's spherically symmetric. We can tell that there is a new type of time dilation or length contraction going on, depending on space and time and position. All this stuff. Yes.
So is there like their own version of time dilation and length contraction for each metric?
Yes. Yes. Because gravity has a tendency to slow down time and to stretch out space. And how much of it will depend on the exact form of the line element. In other words, your metric. So for every metric you have a different amount. But here's something interesting. The normal time dilation, the one that you're used to for Minkowski and Lorentz contraction that you use to Minkowski, that holds in all of them. So in whatever space-time you are, you always have your standard Lorentz contraction and time dilation. You will always, in general, have a gravitational time dilation, gravitational Lorentz contraction, quote unquote. But the latter two depends on what space-time you have. Yes?
And how do you compare different time, like if you have like different details, so yeah, you don't,
Yes.
you can't refer to something.
That is very true. Oh, I love this question. I did not anticipate that one. The question itself. The question is now, if you have two d taus,
Yeah, like how can you refer?
how can you
Not
relate it to each other?
Yeah.
Okay, here's a good idea. So you have some person who is seeing two things happen, the exploding firecrackers. Some other person seeing two things happen, but both of them are at different places in space-time. They both measure different d taus. How do you relate the two d taus to each other? Here's the trick. Take one person d tau related to this guy, dt. Then take the other guy, relate his d tau to that same dt. If you both know how to compare your respective d taus to dt, but you know that dt has to be the same for both, you can relate the d taus to each other. And for that reason, this one and that one, or the observer who is infinitely far away and is stationary, in some books it's called the Bookkeeping Observer. That's the person that you relate your times to, so you can relate it to somebody else's. Bookkeeping Observer. It's like changing. I'll be there in a second, Panos. But it's like changing your currency, right? Suppose that you want to go from I have no in Finland. Is there still? They have euros, no, or they don't?
We have euros.
You do. Oh damn. Okay.
15 years.
Okay. Sorry, I just didn't. I mean, I know there's some exceptions somewhere in
Yeah,
Scandinavia, but
Sweden.
Sweden. Okay, thank you.
Denmark.
Okay, well, they have the what are they called?
Kroner.
Kroner. Okay. Suppose that I have a certain amount of euros and I want to put it into kroners, but I don't know their individual rate, the currency rate. What we can do is I see how much euros I get for $1, and I look how many kroners I get for $1, and then I can make the transition. So the dollar is there to make the other conversions possible. Well, this is the dollar. relate the two details to that one DT guy, infinitely far away, the bookkeeper, and now you can compare them to each other. This is how you do it.
Gold is a better example.
Maybe I should have used gold, because I think in economics this is what they really use, right? We don't have this.
Not anymore.
Not anymore? Okay, it shows what I know about these things. Okay, but you had a question, I think.
Yeah, so can we say that special relativity is general relativity only focuses on specific tensors, on specific metric tensors?
Special relativity only focuses on specific metric tensors?
Is the application of general relativity to specific metric tensors?
Yes. And metric tensor being the Minkowski
Yeah.
tensor, yes.
Okay.
Yes.
Not just one case then? Just the one case where special relativity is defined.
Yes. Okay, lots of insight. After the break, we will put this into mathematical practice. But you're going to learn a lot, right? Just from looking at this thing, even without doing the mathematics. So, all right, second mug of enormous amounts of coffee. Okay. I think I will erase everything except for the line element. And I drew a picture of a black hole over there, as far as I could give it. Just to emphasize, this metric and all the conclusions that we're drawing right now holds for any symmetrical mass distribution. I'm just saying black hole for sensational sake. It also works for Earth and planets and such. It's just that for black holes, the effects that we're going to calculate are much more pronounced. For the very simple reason, it's more easy to get close to a black hole. Well, in practice it isn't, because you have to fly 10,000 light years to get to the closest one, in Sagittarius. But that's not what I mean. What I mean is that the effects become more pronounced the closer you get. The smaller you make R here, right? The closer you get to the center of gravity, that spherically symmetric mass distribution, the bigger this number gets. So the bigger deviation from Minkowski you will get. Now, in practice, before you get to R small enough to get this number to be big, get big deviation from Minkowski space-time, you've usually already encountered the crust of the planet or the star that you happen to be looking at. I mean, literally, just the thing is physically too big for you to get close enough in order to see some sizable effects. A black hole does not have that issue because it all shrunk into this one point, so you can get as close to it as you want. So yes, these effects all exist for Earth, for suns, white dwarfs, all these things, stars. It's just usually you crash onto the surface of the thing, or you burn up in its in its halo way long before any of these effects become sizable. Yes.
Are we gonna talk about the singularity at some point?
Yes, because there's two singularities here, and I'm going to mention both of them. It sounded like this elephant in the room, right? At some point we're going to talk about this singularity. Yes. For a moment I thought I could get away with it, but I can't. In fact, just to give you some idea of how little these effects are, right? I mean, you can read this one and this one as deviation from Minkowski. Before, somebody asked a question if G was Newton's gravitational constant, and it is, which in the usual units is 6.7 times 10 to the power minus 11, so it's a very small number. And then you have to divide it by c squared, which itself is 9.0 times 10 to the power 16, that is squared. So you get minus 11 divided by 10 to the 16, that's about 10 to the power minus 27. So this is a very small number except for the m. So the only way to get any pronounced effect of this deviation is that you counteract the smallness of g and the bigness of c. And one thing of doing that is making the mass bigger. One other way is by closing in, by making r very small. Now again, if you just plug in numbers for the Earth, say, the mass of the Earth is what, 6 times 10 to the power 24 kilograms. The radius of the Earth, the closest you can get before crashing, is about 6,000 kilometers, 6,400 kilometers. If you plug in these numbers, it's ridiculously small.
What do you mean by crashing?
No, literally this. That, here, let me draw a spherical object. Say it is the Earth. Okay. Over here, this effect is very small because r is very big, So at this point, over here-ish, this number is so small it looks just like Minkowski space-time. The closer you get, the smaller r becomes, the bigger the deviation becomes. So you will see some sizable effects at some point, but you cannot get closer to the planet than the actual size of the planet. So this is what I mean. And for normal everyday objects like planets and even stars, this point, the closer you can get before literally bouncing on the thing or burning up in its heat or something like that. Over here, these effects are still not very pronounced.
Yeah.
So this is what I mean when I say that black holes, it's easier to get close to because there's nothing stopping you from getting close. No crust, no surface. So that's why.
All the mass is concentrated
In the singularity, yes.
one point.
Yes. Anyway, so just for emphasis, everything we're going to conclude now is going to be true for all spherically symmetric mass distributions. Again, this is Birkhoff theorem that you can only have one curved space-time for such a situation, regardless of the origin is, as long as it doesn't spin. I tried to draw a picture here. Here's the thing in the middle. Again, it is going to call black hole for sensational purposes. And here's the space-time around it, right? Suppose that this is the x-axis, then this would be your phi in your usual coordinates, and this would be your distance r. Just have some idea of what the thing
It's
is.
not like a flat space.
Yeah, that's because I find it hard to draw three-dimensionally, but no, you're right. I mean, in real life, and again, that's one of the exercises, I will ask you to calculate what happens here to space if you get very close. I already said r is the amount of distance, or dr is the amount of distance as measured by the person over here, far away who is stationary. But if you're close, what does that person measure? You'll find he will measure a bigger distance, and this bigger distance becomes extreme when you get extremely close to the black hole. So this is when things being pulled apart. So this is what you see in pictures, that it's sort of drawn like a hole where this part, the going down part, means that the lengths become strengthened out or lengthened out. Anyway, let's put everything that we've seen into mathematical practice. What we have here, just as a general conclusion that we saw before the break, if you have a random curved space-time, you will always have your usual time dilation and your usual Lorentz contraction due to relative motion. Before we always called it just time dilation. From now on we're going to call it special time dilation. Special because it refers to the special relativity. So this is always true. Or special relativistic time dilation. And the special length contraction. This is always true for any space-time. And it's certainly true for Minkowski space-time, but it's also true for non-Minkowski space-time, and that has to do with this Lorentzian signature. The fact that there is a minus sign different between time and space is, if you remember, if you go back to Minkowski, this is always what gave you time dilation or Lorentz contraction. And since we carry over the minus sign, this Lorentzian signature from special to general relativity, you will always end up with this regardless of your metric. And then, of course, there is the now new thing, gravitational time dilation and gravitational length. Well, I struggle to call it contraction because it could also stretch out. So, no idea what to call this.
Just change in
Yeah, it just changes, I guess. Now these, as we know, depend on relative velocity. This is due to relative velocity between two observers. And this, that we now saw, is due to where you are in the space-time. Due to relative position. One person standing over here, he measures this, the other person stands over there, he measures that, and the two numbers are not the same. Even if they're not moving with respect to each other. So it's not special relativistic, it's location dependent, gravitational, due to relative position between the two observers. And generally, if you have two observers who are both moving, or moving with respect to each other at different positions, you have a combination of both. So time dilation and Lorentz or length differences is now this interplay between two different phenomena. And I want to put this into practice. So, the following situation is one I would like to look at. We don't have to restrict ourselves, but just for example purposes, I'm going to use this one. I'm going to have one person, one observer is going to stand over there. And let's say that the amount of meters from the center of the space-time is capital R, some fixed number. So this is, we have to call this, give this guy a name. Let's call person A. Trying to think of something clever, couldn't think of anything. Now there's another person who is standing over here. This is person B. And, well, you tell me, shall we take that person to be the bookkeeper one, the one who's stationary now moving?
Could be for bookkeeper, yeah.
Oh, okay, well, that makes sense. I mean, in principle, we can also have this guy moving around, or not be at infinity, okay? But let's make this the bookkeeper guy. That's a good idea, B for bookkeeper. All right, great. And here's some other person. One other thing I would like to do is, just to add, no, I'm going to save that for a little later. Let's do it in steps. This guy is not moving. Okay, and this guy is not moving, it's just they're not moving in different positions. Waiting for somebody maybe to ask a question how this guy cannot be moving. He's close to a black hole, right? Shouldn't he be sucked in or something like that? So let's play this game again. Drink my coffee here.
Do we just take this to be like one specific moment in time?
It's a good question. Oh, that's not my question. Sorry?
Do we just like take this to be a very specific, one specific
Oh,
moment
that
in
we
time?
freeze in time? No,
Yeah.
no.
Okay.
So he's literally not moving even if you wait.
So does he produce some sort of counteractive force?
Yes. So let's suppose it's a guy who's in a rocket or something like that, and the rocket is blasting outward while the black hole is trying to suck him inwards, something like that. By the way, the motion of that guy, the B guy, you cannot calculate it with the geodesic equations. Because the geodesics is only if a person only feels gravitational forces. At the moment that I say he's blasting away, I'm breaking that rule.
A guy.
Sorry?
The A guy.
The A guy, sorry, yes. The B guy, well, I think you can do it with geodesics because he doesn't feel anything anyway. Yes?
Is only for curved spacetime and only under the gravity equivalent statements.
Yes. So okay, there's a guy blasting outward. Again, it doesn't need to be, but for our illustration purposes, let's say that he's stationary at this point. He cannot be stationary because the black hole is sucking in, so we're going to use this other force that's pushing him outward. We're not going to bother with this force. Where exactly it comes from, how much fuel he has in this rocket and everything. There's experimental details that we don't care about. The only thing I care about now is the amount of time here versus the amount of time over there. That's the only thing I want to calculate. By the way, is there going to be a special relativistic time dilation here in this setup?
There's no relative motion.
There's no relative motion. So this effect will not be there. So if there's going to be a differences in time, it's purely because of their different positions with respect to the mass in the center. Well, let's calculate it. Let's do it for person. Let's do it for person A first. No, let's do it for B. There's two events, and let the two events be two things that happen at position A, next to person A. Could be Andreas who's exploding twice, or something like that. Yes, just two things happening, two exploding firecrackers right next to this guy. And those two exploding firecrackers are going to be observed by this guy. Question, how many seconds is there between two exploding firecrackers as seen by B?
And sorry, we said A, the time difference is 0, right? They're simultaneous.
No, they're not. There's two firecrackers, they happen at the same position for that guy, not at the same time. what we're going to need is the d tau. Agreed? But it's d tau as seen by person at B. And I hope from the discussion before the break you know that there's no breaking of any rules if we say that there are two different d taus. So there's a d tau, the amount of seconds for the two events, how much time there is between the two events, as seen by this guy, the two events being two firecrackers exploding over there. That is it. For all these d taus you're going to calculate, you can use the line element. It's just you have to plug in the right numbers. Question. What is dr for the two exploding firecrackers as seen by that guy at B?
0.
That's 0. And the d phi, d theta?
Same.
Same 0. So the amount of time between the two exploding firecrackers is given by this, because the rest is 0. This is just me copying the line element and putting in that these two events happen for B at the same position. What is R? There's an R here. dr is 0. What is R?
Distance and B is from the center of the black hole?
No, it's where the guy is looking at it. That's what we also did before. I'm really just repeating the calculation I did before when I proved that dt is d tau for the infinite observer who is stationary. So this r is where guy B is, which is infinity. So by the same argument as before, all of this drops out. You would just get c dt squared. In other words, the amount of time that the guy at B sees between the two exploding firecrackers is really just this number. I don't know what the number is, by the way, but I do know that dt and d tau B are related in this way.
Where are the two events happening?
Here, at position A. Let's play the same exercise now for the person at A. He's looking at the same two events. It's the same two exploding firecrackers. He too sees an amount of time between the two exploding firecrackers, d tau A. Now, question. How much distance is there between two firecrackers as seen by A? That's right?
0.
0. Both in r, in theta, and in the angular and in the radial. The person at position A sees this amount of time between the two exploding firecrackers. Because for him too, the two firecrackers explode at the same position, so this is 0, this is 0, this is 0. What is RA for him?
Capital R.
That's capital R. Right, he sees, oh, there's a c squared missing. He sees two firecrackers from his point. That's, let me rephrase. What you have to put in here is where that observer is, which is at capital A, capital R. Conclusion, d tau A is, take the square root of both sides, divide by c and such. So I got both of these directly from the line element. All information in general relativity always comes from the line element, or if you will, the metric. So I did not have to put anything in, except for information on the two firecrackers. That's all that I did. So two exploding firecrackers, they explode here. This guy measures this amount of time. And this guy, looking at the same two exploding firecrackers, measures this amount of time. Two separate statements, you can combine them into one. The amount of time measured by person A is 1 to mg r squared square root dt, but dt happens to be the time measured by the guy at B, the bookkeeper guy. So there you go. So I've just combined these two equations. So far this is just the mathematics. Yes.
How can you combine these two equations? Like is dt not different? Like dtb is not different than one from A? Like
No.
the time differences?
No.
There's one dt.
There's only one dt.
Okay.
It's like the currency exchange.
Yeah.
There's only $1 that you compare to. I've now related the two amounts of time between the two firecrackers to each other. In fact, this is these means a small, infinitely small amount of time, as if they explode 1 microsecond after each other. And if you want the full amount of time, you can just integrate both sides. Yes. I'll be there in a second. So let's integrate it both and get the full amount of time. You have to be very careful here because I've integrated both sides. That means there was an integration sign over this. In our particular case right now, this is a constant. Because r happened to be at a constant. If that thing itself was moving along this line, r would not have been a constant throughout the integration. In our case it was. So that means the integral only applied to the d tau b. This is a constant and this is what you will get out. You had a question, I think.
Yeah. Since the amount of time between the two firecrackers is the same for A and B,
No.
but dt.
No.
That's time.
Yes, but
Is dt not the time measured? Like okay, that's the first of cracker that exploded, and that's the second, and then
yeah,
you have the
measured by whom?
by B and by A.
No, only by B.
Only by B.
Yes, this is this equation.
Why do we plot it in for A? Why do we use dt for?
Short version, short answer to your question.
Mhm.
They do not measure the same d tau. They also
Yeah, but they are
yes.
the same dt.
Yes.
Why are we bothering then? Like if they say yeah, firecrackers exploded, there's a time difference of 2 seconds, and the other one is like same 2 seconds. Like why are they
Oh
not
no.
bothering?
They have the same number for dt, but this is not the amount of time that they measure on their watches.
So what is the physical meaning of dt in this case?
In this particular case, it happens to be that time measured by the guy at infinity. This is a statement that I made before the break that I said you also have space-times where the dt, or what have you, does not happen to correspond to anyone's time.
Then it just purely exists for the bookkeeping.
It's literally here for the bookkeeping. This is why it's called the bookkeeping time. Now it so happens in our particular space-time, Schwarzschild, that dt is actually measurable time on somebody's watch, namely the guy at infinitely far away. So dt is not the amount of time measured by people. In this particular case, it happens to be so for one of them. In general, it's not. It's the d tau. D tau is a physically measured amount of time.
Okay. So can you say that like in this case, d tau and dt is like inverse from the case of special relativity, that dt was the one measured and d tau was like the general one to which I want.
Well, yes.
Yes, like the other way around. dt
Yes,
is the
yes.
one measured and the d tau is the one measured.
Yes,
and
but
dt.
yes, you can.
Okay.
But only, I mean, I would strongly advise you to be very careful with that rule, quote unquote, because in special relativity, what we did, we took d tau to be the same for everyone.
Yeah.
But that was because we made use of the principle that d tau should be the same for everyone, invariance of d tau, when they are moving with respect to each other.
Yeah.
In our case, they're not moving with respect to each other, so your rule does not generally apply. So this is why I'm saying be very careful with that rule. I fully understand what you mean.
Mhm.
Oh, it's like opposite to
Yeah,
special
that's
relativity.
yeah.
Yes, only for this particular
Yeah,
situation.
yeah.
Okay. So again, be very strict here. If you get given a line element, or if you will, a metric, and you write this out, you will find dt's and dr's and d thetas or whatever coordinates somebody happens to give you the space-time in. this does not automatically correspond to somebody's measured time or space. That is this step. You have to be very clear. If there's somebody who measures these numbers on their watches and their length sticks and such, it might very well be that there is no one who measures these things, and it's purely a mathematical bookkeeping device. It's in our particular case for Schwarzschild where it just happens that our bookkeeping device corresponds to somebody's actual measure time, maybe the guy at infinity.
Is that because we choose B to be at infinity?
Yes, because putting B at infinity here means that dt becomes d tau. So it's the d taus that are measured. It's always the d taus that are measured. It's only a special case that d tau happens to be the dt that comes here.
Okay. I was just a bit confused because I thought of dt measure.
I understand, but I mean it takes a while to get the hang of these things, right? I mean it's very easy to confuse yourself. What do these things mean? In fact, let's do one of these right now. I have now the relationship between the amount of seconds between the two exploding firecrackers as seen by this guy, and that guy. Now, which of the two measures the bigger number? I'm going to put an inequality sign, but I have to be sure that I know which one it is. Which is the bigger number? D tau A or D tau B?
Tau B.
Yes, because d tau A is something smaller than 1 multiplied by d tau B. So this is what you will get out. Interpretation. How much it differs depends on what the values of capital R and or the mass m. Question. Whose time goes fastest? A goes faster? Sure?
No. That's B.
Here's an interpretation thing again. Yeah, this is the difficult part, right? Interpreting the results. All right, there's your two exploding firecrackers. There's you again, and I'm standing here-ish. And you measure how many seconds there are between your A. Well, actually, it makes sense too, right? Two exploding firecrackers, pak bang, and you say it's 2 seconds. Okay? I look at you, I see that happening, I say, no, it's a bigger number. I'm B. That does not make sense, but I mean, I'm B. And I say, no, it's 5 seconds. So what do I observe if I look at you? Do I see you go faster or slower?
Faster.
Faster, right?
Faster.
Less time.
Because the B's clock has more ticks between the two events. So
I'm seeing 5 seconds. It takes a whole 5 seconds before the second firecracker explodes. Then.
Oh yeah, so
then he sees.
you experience 5 seconds in the time that he experiences 2 seconds.
Yes.
So your time is moving faster than his time.
yes.
So if I look at him, I see everything take more time. And not just 2 firecrackers, everything. He blinks his eyes, he rubs his hair, he scratches, he gets gray, he gets older. Instead of 2 exploding firecrackers, you would also say the moment that he was born and the moment that he dies. I see that as a bigger number than he himself sees. I see him slow down. Everything that I see happening over there takes more seconds from where I see it, or more years, than he sees himself. Conclusion. If you look into the Schwarzschild space-time, you look from outside, you look inward, everything here will look slower to you.
Yeah, this is all the sci-fi
So
movies.
it's like an
thing.
interesting.
Yes, but these sci-fi movies are literal in that sense. I mean, this is not a joke. This really happens that way. Yes,
And why does the gravitational lensing elongate planets that we observe?
it does.
But it elongates them. Oh yeah, so equivalent in time would also be slower.
Yes, but we don't measure time when we look at these things because we get all the photons and the time dilation you don't measure.
But we still get deformed images, so that means the photons arrive at different moments, right?
No, the deformation is purely because of the spatial deformation, not because of temporal. Here's an extremely important conclusion. Gravity slows down time. The closer you get here, as in the more you are here, the less time it takes between two things. Or if you will, if you look from the outside, the more time you see things happening over here. So that's how that works.
Can you say that again?
Yes, that if you're looking from the outside inwards a black hole, everything that you see from outside will go slower. Now, here's a story, an actual real-life story. Well, I haven't gone to a black hole, but I read a story once when I was about 9 or 10 or so. It came with this science magazine that I was subscribed to. De Kijk for the people who. Okay, no. So back in the late 80s, 1989 or so, I was 10 years old, 9 years old or so. There was a copy of De Kijk, and it came with a story this time. It's a true story. This. It was a story. It was very sad. I didn't fully understand it, but it was about a couple of astronauts in their spaceship, and unfortunately, like the guy at A, they were being sucked into the black hole, but they didn't have enough fuel to blast themselves out, so they knew that they were doomed. Okay, and so they decided, okay, well, some of us has to survive, but unfortunately, our escape pod only has room for one person. So they drew lots or something like that, and they drew straws, and there was this one person who was fortunate, quote unquote, enough to take the escape pod. He blasted out, went back to Earth, and ended up over here. And then the story was very sad. It was only 3 or 4 pages. Highly made a big impression on me, because it said that the guy was sad that he had lost his friends, but not just that. Every time that he looked at space, he still saw it happening. Because that thing, the radial inflow of his friends into the black hole has slowed down. So it hadn't happened yet. So every time that he looked up, he still saw his friends. No, that is a sad story, but it's true. I mean, this is what physics will do.
So did it ever happen in the end if he still saw it happening for such a long time?
Well, that is the next question. I mean, if he doesn't see it happening, what happened to these? Well, for these guys, here's the local Lorentz frame argument again. For them, time just went on, and they've already passed away. They literally passed through the black hole. It's just over here. It hadn't happened yet. This is not, by the way, because of the light, the information still on its way towards the Earth. That is a separate effect. That's not what I'm talking about. Space-time itself has not made it happen yet. So here's a strange question. How could it have happened for these guys but not for these guys? Well, there's relativity for you.
But
yes?
But it's also the case, right, that if B, looking at A, sees A's time slowed down, if A would look at B, would A see their time speed up?
Yes, that is a good comment. If you're this guy and you're looking outward, you would see this go faster. Mm-hmm. That is true. That is very true. This is different, by the way, from special relativistic time dilation.
It's not reciprocal anymore.
Because over there in time, in special relativistic, there would be reciprocal. That one guy can say to the other, well, you're slowing down, and then the other, no, you're slowing down. And that's because relative velocity is a measure for both. But because we now have a gravitational time dilation that really is different for both, it's not reciprocal anymore. Yes?
So is it possible for the guys in this spaceship going into the black hole to see Earth advancing thousands of years?
Yes. Not just possible, that's literally what happens.
But also the ones on Earth see them constantly almost about to die.
Yes. This is the sadness of that story. Then again, the good news for these guys is at least we see what happens to the rest of the world.
How is the information able to go both ways and not have two completely separate outcomes? Basically.
I understand the question. I'm just wondering if there is a contradiction there. I would have to think about it. I mean, the first question is there a contradiction? Because you frame it as if this cannot be that information has gone one way ultra fast, in other way it's gone ultra slow. How does that happen? Yeah.
I feel like the information traveled through time, basically.
Yes.
Like forward thousands of years one way, or then because the civilization from B hasn't lived thousands of years yet, but they still see them dying. But
okay.
Like an information being instantly created.
Yeah. Kind of. Like, how do the ones going into the black hole know what's going to happen on Earth in thousands of years?
No, I fully understand, but we're assuming here that there should be no creation of information If the amount of creation per second of information for one observer should be also that of the next, or something like that.
Yeah.
But I'm not sure if that is an issue, because in space times, no, one step back. In normal physics, non-relativistic physics, there's only one time.
Yeah.
And what you lose in space, you get back in time. That's the idea that the eigentime should be invariant. So I'm not too surprised that you find that if you squeeze in space, you get back more time and also more information in time. I mean, just thinking out loud now, I'm not sure if there's an issue, because the total amount of information is scattered over space-time. And the paradox comes from the idea, but there's more information per unit of time for the both. But it's not information per unit time, it's information per unit of space-time. And there might not be an issue there.
Okay.
But this is my short answer. I would have to think about it. I'm not sure if I...
Yeah, like the little problem I have with it is, or the way I see it is, basically nature knows what's going to happen on Earth in the next
Oh, no, that- no, yes, yes,
that
that is-
happen in the next 1,000 years.
That is very true. That answer I can give you without hesitation. Everything has already been frozen into space-time, if you will. It's just that we, in our particular spatial frame, have sliced it in such a way that you can only see certain moments in time. One way that I once read it in a book, it's this, and I like that idea. It's a conceptual idea. It was from a book on popular science. Is that they compared the whole of space-time, everything in it, everything that happens at any position at any moment in time, as a loaf of bread, where this is the amount of time, and this would then be one of the directions of space, something like this. And in Newtonian physics, what you would do, you would slice up this bread, you would slice up one slice of bread here, and in this slice, you can see all the things happening at the same spatial position. But if you would slice, I don't know how to draw this, but you can also slice it like this. Diagonally. And what you then get is that what you've lost in amount of spatial information, you get back in temporal information. But all the information of the whole of the universe is all encapsulated in that loaf of bread. It's just how you slice it, quite literally in this case. But we were doing this already when we were doing Minkowski space-time, because I said what you get, remember this picture that I drew, that this is dt, this is dx or something like that? And this number should be the same for all. If I change the angle, I lose a little bit the x, I get back a little bit of dt. That's really this picture again. So the short answer is all information is already in there, and your confusion, well, wait a minute, how does that happen if there's more information coming inward and outward and such, is because you're only looking at the temporal part of the information, not the spatial part. I think that's the answer. Yes.
So the guys at A who are being sucked into the black hole.
Yes.
If they look to where the Earth is, basically.
Yes.
So if you would then link that to the loaf of bread, then the slice they would have would be basically like this, right?
It's more complicated here, because the slice that nowadays is just special relativistic. You also have to rotate the loaf of bread. So regardless of slicing, there's also loaf of bread that comes with its own shape.
Yeah. Okay. So.
Yes.
Is it possible for special dilation and contraction to cancel out gravitational dilation?
Yes, actually. Yes.
Like perfectly to
Yes. And that is a fun exercise to do. In fact, let's take that one, because my next example was going to be, let's have A move now. We now had him in a fixed position, yes? Let's see what happens, time dilation, but now we're going to introduce special relativistic time dilation because of relative motion. So this guy is still stationary, and this guy is now moving. Right? Oh, by the way, do you see that there's something beautiful happening here at the moment that you get to a particular position of R? The R that makes this whole fraction be unity. mean, there is an r, a certain amount of distance. If you plug that number in, then this whole fraction here becomes 1. You get 1 minus 1.
Is that the Schwarzschild radius?
That's the Schwarzschild radius, or the event horizon. What does it say about dTA, d tau a?
That is d tau b then at that point. Right?
No.
Oh, it's 1 to the minus 1.
Yes, so?
0.
Alright. So there is...
Oh, I thought you meant the
No, not the
whole-
fraction, the whole thing.
thingy. Yeah.
If you do the math, if r happens to be this number, then this fraction becomes 0, or the square root becomes 0,
Yeah.
so you would get d tau a is 0. That means that between the two firecrackers, there are 0 seconds, as seen by this guy, if he is at that particular distance.
You experience the universe's lifetime.
Yes, because we already saw if he looks outward, he sees the rest going faster. In how many seconds? 0. So he sees all of the rest of the universe happening in 0 seconds. He sees literally all of time.
Well,
in
like
1
past
second.
and the future.
Yes, past and future, goes both ways. So there's something beautiful happening here. The event horizon, people say, well, this is the place where light does not come out, which is true. It's also something much more beautiful. It's that thing that if you happen to be standing over there, you would see everything that would ever happen in the universe come at you at once.
If you were standing at the event horizon.
Yes, at this particular distance, the Schwarzschild radius or event horizon.
Well, what is the distance like towards the black hole?
Yes.
Well, in the black hole.
It's that's a matter of terminology. The people typically call this the radius of the black hole.
Okay.
And there's more theory behind that. And just as a very short answer, and so I just giving you short answers, but if you get closer than this number, notice that then this whole thing becomes negative. Do you see that? And this thing becomes positive. So that means that space, radial space, and time have switched sign. So that means if you go inside a black hole, what used to be your time component has now become a space component. And the other way around. Yes. This is deep stuff, but fortunately you don't have to worry about these things, because in order to measure these things, something has to come out, and it can't. This is also the moment where nothing happens. Okay, one more funny factoid about black holes. People always say, well, it's such a crappy thing. If it goes to a black hole, it will be ripped apart, which is true. One of the exercises of the tutorial is to calculate what the distances do when you get close to a black hole. You will find that it gets ripped open. This is what I try to draw here. And people say, well, this is bad if you go close to a black hole, you'll be ripped apart. That is very true. But suppose you would survive that. There's a sucky thing there, that because even if you survive that and you manage to get out, suppose you were not in the black hole but close to a black hole, and you manage to get out again, everything else has already happened. So you come back into a world where everybody that you ever knew and loved and such is not there anymore, because time has moved on with much more rapid pace outside.
Then where would you draw that line? Where would you come out again?
Well,
Because
that is okay. Yeah, that is.
everything has already happened.
No, that is very true. So what I should say is, if you're infinitely close to that radius, because if you're on it, then it's going to be 0 seconds. Okay, so there's what is coming out of something. If coming out requires time, which there isn't anymore, something like that. So let's say you get close enough that something happens, but not so close that that question becomes relevant. There's a nice movie about this that you might have seen. It's called Interstellar, where the premise, I'm not giving you any spoilers because this is really what the movie starts with, is about a guy who has to go to a planet close to a very strong star. It might even be a black hole, I don't remember. But to do some operation there, I forget what he had to do. I think he had to check whether it was suitable for colonies or something like that. But he didn't want to do it because he knew from general relativity that his time would go slower, this time would go faster or move on with his normal pace. And he was afraid that if he would come out from his job, he wouldn't see his daughter anymore because she would be gone. So he only wants to do the job if he could only stay there for a while, and when it comes out, I don't know, 60 years have passed or something like that. So, but this is real. This is real. This is what physics does. Okay. So we've seen a lot of things now. This is the gravitational time dilation. You can see it becomes extreme at the moment that you are at the Schwarzschild horizon. If you stay outside of it, it becomes more pronounced the more you close in. And most important upshot, A, there is gravitational time dilation, and B, gravity slows down time. The closer you get to the source of gravity, the slower time will go for you.
So if you choose R to be 0, we get d tau A equals infinite.
Yes, but
Or doesn't mean.
okay. Well, here's the elephant in the room. Okay, if R itself is 0, you run into a different problem because then you have two infinities here, and you cannot do mathematics with infinities. So that means that there's.
Yeah, you just made a statement.
Yes.
If you were inside the black hole, you made a
Yes.
statement about the outside, but now you said we can't really
Wha-
explain what's going on.
No, what I said was, if you go inside the black hole, funny things happen. But you made a more explicit statement. You said if you go at R is 0.
All right, so that's if you go beyond the
Yes,
parcel.
not just beyond this, that you make r, small enough that you're actually at the center of the black hole. Then this becomes meaningless because you have 1 minus infinity, and you have another 1 minus infinity, and you cannot do mathematics with these things. Now, before that time, this is of course a big branch of physics right now, theoretical physics, is, well, there should be some quantum mechanics happening at some point because things get very close to each other. So in order to really understand what happens at R is 0, you can clearly see this does not work anymore. And the idea is maybe with some quantum mechanics we can solve that, but nobody has figured out how to do it.
You need a quantum theory of gravity.
Yes, and it doesn't exist. And of course people are working on this, and the people who can find a working and testable version of quantum gravity can go to Stockholm and pick up his 1 million kroner and get a Nobel Prize for this. So there are some open questions. Outside the black hole, by the way, you can fully do this. You don't have to worry about quantum mechanics. You can just do these tricks. Okay, now I promised we're going to do one more example. Namely, we're going to have this guy, person A, now move around the black hole. And just for simple purposes, because it makes it more easy to calculate, if you want to do a more elaborate example, feel free, you know how to do it now. But let's say that he moves around the black hole in a circular orbit. Circular orbit around the black hole. So question is the same, what is the time dilation between the two observers? And what is the exact formula? One observer is still the bookkeeper, so this one will still hold. We don't have to change this. The only thing we have to change is the calculation for A. And then we play the same trick. Then we relate these two things to each other and see what the overall time dilation is. Already you can tell it is going to be a gravitational time dilation because there are at different positions within the space-time. And there's going to be a special relativistic time dilation because they have a relative motion. All right, let's do this thing. Again, we're going to calculate the d tau for person A. Let's say that it moves in a circular orbit of radius r. Not Schwarzschild radius, just a radius r bigger than the event horizon. Circular orbit. And let's also say that he does it in a flat plane. What does it say about dr? It's 0, because he stays at the same r. D theta, also 0. D phi, non-zero, because this is phi, and his phi is different at any moment in time. So we're going to use the line element again. If you know the line element or the metric, you know everything, so we should be able to figure this out. C squared 1 minus T mg r c squared dt squared minus, we saw that this is 0, the dr, because he stays at a fixed radius. That's by definition a circular orbit. This one is 0 because it stays in one plane. This one is not 0. Oh, we have to choose a theta, by the way. Theta is the angle that this plane has with the z-axis. You choose whatever you want.
Isn't it simply if we set it as 0?
No, d theta is 0. Theta itself does not necessarily have to be 0.
But if it's like in the plane, then it's not like.
Yeah, but plane with respect to what angle? What axis?
X?
Yes. Theta is with respect to z. That's the definition of the thing. Now, if you remember from the Minkowski spherical coordinate calculation that we did, we were not allowed to choose theta is 0, if you remember that. It was a mathematical reason, because then the Christoffels blow up. It's not because there's something strange going on at theta is 0, it's simply because we made a choice for our coordinate system. And in spherical coordinates, it just happens that we introduce some infinities there if you don't was careful.
Pi over 2?
Yeah, we take pi over 2. You don't have to. You can choose any other number as long as it's not 0. So that makes sine theta then becomes 1. If you don't like that, feel free to use any other theta. That's fine as long as it's not 0. So this is what we get now. Again, d tau a is the amount of time between two things that happen for the guy at A. And you can see there's something else now that happens. Before we had this, we now have an extra term. Let's write it out. This is just mathematics that I'm doing now, no physics. C squared I divide away, get 1 minus 2mg rc squared d tau squared just a rewrite of what we have. Right, just take the square root of both sides and such. I divide it out to c squared, ends up here. One more step. Just algebra, no physics. In the first step, I just took the square root of both sides, divided by a c squared. Second step, I took a dt out of the whole square root. What would you call this thing? d phi divided by dt. Physically, what is that thing?
Angular velocity.
Yes. Measured by whom, by the way?
The person B, because we're using we're not using
The bookkeeping.
Yes.
Yes, it's the bookkeeping guy. It's the amount of angle that person A makes in an amount of time, dt, and that was the time measured by the bookkeeping guy. So it's the amount of angle measured by the bookkeeping guy divided by his amount of time. So that's what he would call the angular velocity of that thing. An angular velocity we typically call omega or something like that. And let's put a letter there, B. It's what the bookkeeper measures. dt. Well, that happens to be the bookkeeper time, right? So all in all, what I get is this. Here's the time dilation between these two observers. I just went through the math, didn't put any physics in. So far so good? Because I would like to go to interpretation now. This part we already knew. There was a gravitational time dilation that was there because there were different positions. That was the one that we had before, when A was not moving. Now that he's moving, another part comes in. That's this part. So here you see two time dilations. One due to gravity and their position. So this position of person A, right? It's capital R. And special relativistic time dilation, because they're moving. They have a relative velocity, the two observers. Which one measures the biggest number?
So what's capital R again?
Capital R is the radius of the orbit, yes. Who measures the biggest number?
In the second argument, is that the space contraction taken into account? No?
You don't have to.
You don't have to.
This is the R, the distance from here to here, and we already identified that R is the distance measured by this guy.
Okay.
So it's your effect is already built in. The question: which of these two numbers is the biggest of the two?
It's still going to be d tau b, right?
Yes.
Yes. Just like before, it's just it's more so now.
Yeah, because the extra term you have now can never be negative.
Yes, exactly. This is always a positive number. So you're already subtracting this due to gravitational time dilation, and you're subtracting more because of your relative motion. So it goes even slower then. So if you're looking outside at a moving planet around a black hole, it goes slower because it's close to a black hole, and because it's moving. So there's a double time dilation, both working the same way. And Panos, you asked if you could also have this time dilation be counteractive, that there should be a plus sign here. That exists too, but not in this particular case.
So the minus sign makes them complementary.
Yes. Yes. I have two more comments and then we should be done for today. So, or if there's any questions. Yes.
A bit off topic-ish.
Okay.
But is there also time dilation and length contraction due to a relative acceleration?
No, there isn't. No, and it's rarely, if ever, specified when people follow a course in relativity, general and or special, that the only effects can come from position and velocity and not from acceleration itself.
I was just looking at
I understand.
Velocity, acceleration.
I know, you see some hierarchy here, yes? Position, velocity, you would expect acceleration. It's an assumption that there isn't. But it's an assumption, it might be wrong.
Really?
Okay. Yeah, yes.
So that extra time we have now, is that some sort of general relativistic gamma factor-ish thing?
It's actually just a gamma factor.
It is the gamma.
Yes.
Because it looks
Very
Is that,
different.
I see a velocity squared over c squared.
Yes.
Yeah, it's just an
and
already
then
angular velocity.
Yes. If you have an orbital velocity of something moving in a circular orbit,
Yes.
how do you, there's a formula for that. Orbital velocity v is the radius times the angular velocity.
Yes.
So this thing, this thing,
That is your v.
that is v squared. So if you will, you can replace this by v squared over c squared.
Yeah.
And now we come to something beautiful. Suppose we have this general situation now. Let's remove the black hole. Right? We have calculated this. Works for every m, so it should also work for m is 0. You get your gamma factor back. This is what I promised. In a general metric, you always have special relative. You always have your gamma factors automatically included. You don't have to do this by hand. It goes automatically. If in case you don't remove the black hole, but you remove the relative motion, put your hand here, you get our gravitational time dilation back. So this is a combination of this full time dilation here. It's everything. This is how you do it. There were two comments I wanted to make. This was one of them. And I forget what the other one is. Well, let's take your question then, Panos. You asked before if you could counteract these things. Yes, you can. In order to do so, what you should have, and as a fun exercise for yourself, what you can do is introduce another observer. It's called C. Let him also move here, and compare these two to each other. Then, you use the bookkeeper guy. So both of them relate to the bookkeeper guy using this formula, and then you relate it to the two. Mixing up my words. I mean it perfectly well, but it doesn't come out right. Let me start over. You have another observer here. Let's go see. Also say in a circular motion. Doesn't have to be, but just do it so we can use the same formula again. Then you will get two copies of this formula, one for d tau A and one for d tau C. Both of them will have the same d tau B in it. So you can eliminate that and you get a direct relation between d tau A and d tau C. If you work out the math, you will find that their relative time dilation is again a combination of gravitational versus their relative motion, and then you can find that they can counteract each other. In fact, if you want, you can blast your rockets in such a way that C moves with exactly the velocity to make sure that all time dilation is gone.
So those classical laws would apply
Yes.
near a black hole.
Yes. Between these two observers. You can already see why, by the way, because we already saw that if you get close to a black hole, time slows down. So A is a slower time because he's close to the black hole. But if you make sure that this guy moves so fast that his time slows down due to special relativistic time dilation, you can make the two counteract each other, and they have the same time. This guy has to do a lot of blasting, by the way, to counteract. So slower, because this one is slower his time because of gravitational time dilation. If you want this guy to be just as slow in his time, make sure that he goes fast enough so his special relativistic time dilation does it for you. So the answer is yes, you can make them counteract each other. So, ta-da! Now this is black hole physics. Great. Cool. All right. Well, we have a tutorial coming up with a
5 minutes.
presentation, and which is now already in 5 minutes. What you do? Make it 10?
Yeah.
Yeah. Any questions so far? You should be able to do these calculations now yourself. It's take this thing, apply it in the right way, plug in the right numbers at the right places, then go through and compare things to each other. And a series of exercises. Yes. If no more questions, let's have a break. See each other in 10 minutes. All right.